Hey Dr. Lane, welcome to section 5 video for physics. So this is a problem I'm showing here. We got two ropes acting on a box and we're pretty much figuring out the force of the rope, the two ropes. That's what we end up really doing after all these different problems. And so first we got to draw the free body diagram. I like to think this is the force diagram because that's what is mostly included in the diagram, is the forces from the center of the object. So we got rope 1, rope 2, which I labeled T1, T2, and they're pulling the box at this direction and this direction. And we got theta, which was given 38 degrees, the mass 40 kilograms, that's the box, and the force of gravity is the only other thing not included in the diagram that is being acted upon to this box. So B asks us, what is the momentum? No, what is the derivative of the momentum of the box? Is it 0 or non-zero? Well, derivative is the rate of change. The momentum of something that is motionless is automatically 0. So intuitively, you can just think of it as the rate of change of something not moving would obviously be 0. The rate of change is none. It's not changing. It's staying the same. So, but here's how you do it. With formulas and math and not just thinking about it. But since here's really where the intuitive piece comes into play, the velocity of something not moving is 0. So of course the momentum is going to be 0 because there's no velocity. And C asks us, what is the y component of the gravitational force acting on the box? So the y component of this vector here, which is negative mg, negative mass times the gravity constant. So the mass, 40 kilograms, plug that in, 9.8, negative 392 newtons. All right, easy stuff. And now D, what is the y component of the force on the block due to rope 2? So that'd be the force going straight up this way. And intuitively you can figure this out too, because since this is not moving up or down, it's motionless, the force going up has to cancel out exactly the force going down. So of course it'd be just the opposite of the gravitational force, which would be 392 newtons. Or you can look here for the mathematical thinking of it, formulaic representation. So that's there. Just because I wanted you to see that, because I did the same thing for the end. And let's see, so we did D. So E, what is the magnitude of F2? The length of this vector here. So we got to use some trig for that one. So we know the adjacent length here, but we don't know the hypotenuse. And cosine theta is adjacent over the hypotenuse. So cosine theta is T2y over T2. And we know T2y because we just solved that. So you just plug that in to the formula here. 392 newtons over cosine 38, you get 497.455 newtons. So that's the length of this here. All right. So E, what is the magnitude of F2? Wait, isn't that what I just did? Yeah, so F. What is the x component of the force on the block due to rope 2? The x component. So we have to use some more trig here. So the x component of, so that's this piece here. So tangent is opposite over hypotenuse, which I think is what I did I not? Oh no, that's opposite over adjacent. Okay, so sine is opposite over hypotenuse, so you just plug those in. That's the opposite is T2x over hypotenuse, we just found that. And you just multiply that out, that's what you get. And then G, what is the X component of the force on the block due to rope 1? The force on the block here. So it has to exactly cancel out this one. So with the same exact thinking, it's just the opposite of this X here. Or you could just do this same formulaic representation. I'm sorry I went over 5 minutes, but I had a lot I had to say. But yeah, there you go. Problem 7 from section 5. Thank you.